Hi everybody, welcome back from the break. I hope everybody had a great break, and I'm really glad that we are able to have class again. Today begins our unit on equilibrium, which is an extremely important topic in AP Chemistry. Like I told you guys earlier, thermodynamics, kinetics, and equilibrium are the three most important topics, and they're all intertwined. So today begins our discussion of equilibrium, which is going to continue on into March. It's a very big topic. So our essential questions for today are: how do we define an equilibrium system? What is it? When we say equilibrium, what do we mean as chemists? What makes some reactions go to completion and not be equilibrium reactions? And what makes other reactions equilibrium reactions? Why is it that I've never heard of equilibrium, but I took chemistry for an entire year? What is happening on the molecular level? What are the molecules and the atoms doing in an equilibrium system? And then what conditions, what variables affect an equilibrium system? So we're going to start by defining an equilibrium system. And the first thing to point out is that an equilibrium system consists of two reactions, and those reactions are opposites of each other. There's a forward reaction and a reverse reaction. And the reactants of the forward reaction are the products of the reverse reaction, and the reactants of the reverse reaction are the products of the forward reaction. And we're going to try to give some examples of that so that everybody will see what I mean exactly by that. And that system of those two reactions is at equilibrium when the rates of the forward reaction and the rates of the reverse reaction are the same. And you want to think about this as every time some reactants go this direction, the exact same amount of products go back the other way. Reactions don't start off at equilibrium. They go in one direction for a little while until they reach equilibrium, and then the rates are going the same way. One thing I want to point out is that does not mean that there's the same amount of reactants and products. That doesn't mean that you have 5 reactants and 5 products, or 10 molar reactants and 10 molar products. It means that you can imagine on the arrows on the bridge in between the two reactions you have the same amount of traffic going in both directions, but it doesn't mean that there's the same amount of reactants and products. This equilibrium system contains both the reactants and the products. If you don't have reactants and products, this is not an equilibrium system. The reactants are reacting to form products, and the products are reacting to form reactants, and both of those processes are occurring at the same time. And if you're at equilibrium, they're also occurring at the same time and at the same rate. So when we talk about rate, we remember that that brings us back to our kinetics, everything we talked about with kinetics, where the rate of reaction equals K times the concentration of the reactant to some power. So it's the same idea. You have two rates, two reactions, each with a rate, and at equilibrium, those two rates are equal to each other. That make a reaction really not reversible. So in an equilibrium system, you have two reactions that are going back and forth, but that doesn't always happen. Certain things can make a reaction not reversible. Transfer of electrons. So if you take electrons from an atom with very low electronegativity and they're transferred to an atom with very high electronegativity, it's unlikely that that reaction is going to spontaneously go in reverse, because it would take a lot of energy to remove them back off of the highly electronegative atom and give them to the one with low electronegativity. So if you transfer an electron from potassium to chlorine, the likelihood that that is going to go back the other way from chloride to potassium is highly unlikely, and it's definitely not going to happen spontaneously. Others deal with separating something from the rest of the reactants and the products. So when we define an equilibrium system, we said that it had to contain the products and the reactants in that system. But if something is leaving the system, then it's not at equilibrium. The system is not going to stay at equilibrium. It's just going to keep going in one direction. So an example is evolution of a gas. So if you have a gas, let's say you have some sort of liquid in a beaker, and then gas is just bubbling out of that beaker, it's continuously being removed from the equilibrium system. Now, one way to keep it at equilibrium would be to put a cover on your beaker, and then you wouldn't be removing the gas as much. Formation of a precipitate. So if you have a liquid and then all of a sudden stuff is in a solid, that's in a different state and it's not as reactive with the liquid state that it was in, or gaseous state. And then the last one is formation of water. This is a common driving force for acid-base reactions. Water is a very stable compound for a variety of reasons, but it's mainly because it has a very, very negative enthalpy of formation. So it's very unlikely that that water, those bonds, are going to break apart and that anything's going to have enough energy to break that water apart and run that reaction in reverse. Equilibrium occurs when reactions, one form of the reaction, either the forward or the reverse, doesn't really have a driving force. So none of these four things are occurring in the reaction. The reaction still happens, but it's not driven in one direction. Typically one side of the reaction is more favored, and that's the side that has a more negative delta G. So that will be the side that produces more. Either the forward is favored or the reverse is favored based on the value of delta G. When we're talking about having one of these four driving forces, we mean that one side of the equation has an extremely negative delta G, and therefore the reverse reaction is very unlikely to happen. All right, and right across the river from us is West Memphis. And every day, lots of people drive to work from West Memphis to Memphis, and lots of people drive home at night from Memphis to West Memphis. But our population is relatively steady. We've got our population of Memphis as 653,000 approximately, and West Memphis about 25,500. And there's a ratio there of 26 people in Memphis to 1 person in West Memphis. However, so for every 26 people in Memphis, there's 1 person in West Memphis. However, those are not always the exact same people. Sometimes somebody may move from Memphis to West Memphis. But over the course of years, these populations have been relatively steady. Both are slightly increasing. But the overall ratio of 26 to 1 has not changed significantly in any recent years. And you want to imagine the bridge as the reaction occurring, the rate of people going across the bridge from one side to the other over time has to be pretty steady in order for the populations to remain the same. So yes, at 8 o'clock in the morning, there may be a mass exodus from West Memphis, and vice versa at 5 p.m. from Memphis to West Memphis. But over time, our ratios kind of stay the same, and the rate of back and forth is approximately the same. Moving from West Memphis to Memphis, Memphis to West Memphis stays about the same over time. Is it the same at every single instance in time? No. But if we were to measure these things over and over again for long periods of time, we would see that this is an equilibrium system. So you want to imagine one side of the bridge is the reactants, the other side of the bridge is the products, and the bridge itself as the forward and the reverse reactions occurring. So now let's look at a chemical reaction that's in equilibrium. So this is an animation of a chemical reaction that has 2 reactants and 2 products. And they're listed as A and BC and AB and C. So you can see as before we start the reaction, the only thing that's present here in my reaction vessel are the reactants. And then once we start the reaction and everything starts moving and colliding, which is of course, as we know, molecules have to collide in order for a reaction to happen. That's how things work. We start to see the appearance of reactants. As you can see the reactants in the reaction vessel, and you can see in my bar graph over here what's present in the reaction vessel. And then at a certain point, we stop getting more reactants. In fact, some of the reactants even turn back into products. We kind of go back and forth, but at no point do all of my reactants turn into products. And part of the reason is the temperature at which I have this reaction vessel. If you look at the reaction coordinate diagram at the bottom right of this, you see where I have my green temperature line, and it's pretty close to the activation energy of both the forward and the reverse. So at this temperature, both of these reactions, the forward and the reverse, have a pretty negative delta G, and they're able to go either way based on activation energy. So in this situation, the reaction is just at equilibrium. It doesn't go in any particular one direction. At first, it goes only forward because there's only reactants. It can only go forward. But once products are in the container as well, it also starts to go in the reverse. So now we're going to look at a different way of representing what was represented on that bar graph in the last slide. So here what we see is the concentration of a reactant and a product. And I want everybody to just think for a second, which one is the reactant and which one is the product? Okay, I hope you were thinking. The reactant is the one that's in there to start with, so that would have to be the blue one, which is labeled as P. Okay, and then the product would be the one that starts with a concentration of 0 at time 0, which is the pink, and that's labeled P. So what you have is a situation where we started with the blue and none of the pink. Okay, and then over time, the forward rate is much faster than the reverse rate. But over time, these concentrations come to a point where they're at equilibrium. And the forward and the reverse are essentially the same. And that's when the line starts to flatten out. Now, I want to point out one thing about this graph that I said previously today, that these concentrations are not equal. Okay, notice, the pink here towards the end of this graph is almost at 1, and the blue is nearly at 0. Those are clearly not equal to each other. So an equilibrium system does not mean that the concentrations of the products and the reactants are the same. What's the same is the rate of back and forth between each one. So now we've looked at several equilibrium systems and what that means. So now let's talk about what happens when we mess with an equilibrium system. Because systems don't just live in isolation where they're never messed with by outside interference, particularly us. And there is a principle, LeChatlier's principle, that is all about what happens when you mess with an equilibrium system. And LeChatlier's principle states that when you stress a system, the system is going to shift to relieve that stress, and most importantly, to re-establish the equilibrium. Okay, so that's very important. Yes, the system is going to shift, but where it is going to end back up is at equilibrium again. So in this graph, it's very similar to the last graph that we looked at. What we're seeing is an equilibrium system that is being repeatedly stressed. And the way that this equilibrium system is being stressed is the blue reactant is being added more of. All right, so at first at time 0, we start off and we have 0 of the red of the product. We have some reactant. The reaction occurs and we reach equilibrium. And then, while we're at equilibrium, all of a sudden we add more reactant. So now that makes the forward reaction go more. And the way you want to think about it is this. If you have more reactants in that vessel, what is more likely to collide? Reactants or products? And of course, it's reactants. The more reactants you have in there, the more likely you are to have a forward reaction. And just to be clear, for the AP exam, they want you to explain this in terms of collisions. They do not want you to just say, because LeChatlier's principle says so. They want you to explain there's with more reactants, there's more likely to have reactant collisions, therefore our forward reaction is going to happen faster. And we're going to shift toward the products. All right. So then our amount of reactant decreases because the forward reaction is happening faster than the reverse. Our amount of product increases and equilibrium is reestablished. All right, and notice that equilibrium, just like our West Memphis equilibrium, it's still that same ratio. So the West Memphis equilibrium was at a 26-to-1 ratio. This is at whatever ratio it's at, but it's the same ratio. Is it the exact same concentrations? No, it's not, but it's the same ratio of reactants to products. So then for a second time, all right, we add more reactant. And because those reactant molecules are more likely to collide with each other, that forward reaction happens faster to produce more products, and it continues to happen faster than the reverse reaction until the system reaches equilibrium again, at which point both the reactions happen at the same rate. So let's talk about a specific equilibrium system and the different stressors that can be applied to it besides just adding more reactant. So in this system, this is something we're all very familiar with. We have nitrogen gas combining with hydrogen gas to form ammonia gas. So we have an all gaseous system. Notice that I have my arrows going in the two opposite directions to indicate that this is an equilibrium system with a forward and a reverse reaction. And I also have our enthalpy there. We have negative enthalpy, which of course means that this is exothermic. So pressure is a variable that only affects gases. Pressure only affects gases because gases are the only state that is compressible. Likewise, this is why volume only affects gases. You can pressurize a solid or a liquid or try to change their volume all you want to, but they're not compressible. They don't change volume. Liquids change shape, but they still don't change their volume. So with a pressure, if you increase pressure, you disfavor the formation of gases. So if we look at our reaction here, we have 4 moles of gas on the reactant side, and we have 2 moles of gas on the product side. So if we were to increase the pressure, we would favor the formation of more products. And that would shift our equilibrium. The forward reaction would be favored, which would shift our equilibrium toward the products until a new equilibrium was established. Now, if we were to decrease the pressure, the reverse would happen. More moles of gas would be favored, so the reverse reaction would be favored, and we would have the more of the reactants being formed. Volume works the same way. When you increase the volume, all right, the larger the volume you have, the more space you have for this reaction to take place, the more gases are favored. So if we were to increase the volume, we would favor the reactant side of the reaction, or the reverse reaction. The reverse reaction would occur in order to produce more and more gas to fill up that volume. The other way you can think about it is that in that larger volume, you are less likely to have so many moles of gas colliding together. Instead, you're likely to have fewer collisions. Also, if you were to decrease the volume, all of a sudden everything's going to get very tight, right? And the N2 and the H2 are going to be much closer together. You're going to have more and more collisions between those, and you're going to have a shift toward the products, or the forward reaction is going to be favored. All right, if you are to remove a reactant or a product, the equilibrium is always going to shift in the direction that you removed it. So if you remove NH3, you're going to form more NH3. If you remove N2, you're going to form more N2 and H2. All right, and I want to be clear here, you still get more hydrogen, all right, because you can't just run the reverse reaction without forming hydrogen as well as the nitrogen. All right, if you remove hydrogen, you're going to get more nitrogen and more hydrogen. Okay, in order to reestablish that equilibrium ratio. And then temperature. Temperature primarily affects reactions based on their equilibrium, based on their enthalpy. So here we have an exothermic reaction. So we can imagine that heat is a product here. So if we were to increase the temperature, that means we add more heat. So we add heat to those product side. Well, if you add more product, you're going to get more reactant. So if we increase the temperature of this reaction, the reverse reaction is favored. However, if we were to decrease that temperature, right, heat's a product, we remove some of that heat. Right, imagine it just like another chemical. So if you have heat as a product and you remove some of that heat, that forward reaction is going to be favored to form more heat. Now it's time for you to think about this a little bit. I'm not going to tell you the answers right now, but we will go over this tomorrow in my video tomorrow. So just think about each of these stressors that I have listed here and how they would affect the equilibrium of this system that is shown. So now, did you learn what it means to say that a system is at equilibrium? How can you predict which way an equilibrium system will shift based on a different stressor? And what makes some reactions equilibrium reactions while others are not? If you can, then that's great. Check out the next slide also for some logistical information about what's due and when, and what all handouts and everything like that you should have for this unit.